I'm going to start the recording, and before I lecture, I'm going to solicit questions. Are there any questions in particular about this week's homework due tonight at 11:50 time? 11:59, sorry. Can I show how to start number one? Yeah, we can talk about number one. I'm going to talk about something really similar in the lecture, and I pointed out an example problem in the link that talks about the whole concept of normalization, which actually came up briefly the other day in the lecture notes, which says that when you take the wave function and multiply it by its complex conjugate, then it's a probability distribution function. And to be a good probability distribution function, when you integrate it over all possible values of the position, you should get a 1. Normalization and factors involving normalization pop up throughout the course. One thing that commonly appears in a function is this thing, which is a normalization constant. In other words, the value of this thing is set to make sure the function is normalized. Okay, so here's our function, and you want to normalize it, which means basically going to solve for this thing. And you're going to do that by taking the integral of this thing times its complex conjugate and setting it equal to 1. Now, this thing is real, so the complex conjugate is pretty easy. You just take the square. And so you'll be making the integral of a squared x squared 6 minus x squared. Further, not all the values of x you have to worry about in this case. It's only not 0. As you'll see, like the particle in the box, it's only not 0 in a certain range. This point 0 to 6. Oh, and then, you pull a squared out front. You're allowed to do that. X squared 6 minus x squared dx, and set it equal to 1. Then you can find a value of a for the function. Okay, that's my hint on how to normalize. You're also supposed to sketch a plot of the function and the square, which is what you're integrating. I suggest sketching a plot of the function first and, just plugging some points in. Questions on what I've said here? Okay, can I take questions on other problems? Oh, for question 3, you keep getting it. It's not an eigenfunction. Well, I guess the question is it an eigenfunction or not? But you're asked about 2 operators. I can ask which operator or both. Let me come down to the function. Okay, down here is problem 3. The function is e to the I 2x plus e to the minus I 2x. It's an I. It's an I. And you're supposed to test to see if it's an eigenfunction of two operators, the Hamiltonian and the momentum operator. Oh, all right. Just for clarity, remember the one-dimensional Hamiltonian's the second derivative operator multiplied by a constant. Momentum operator is the first derivative operator multiplied by a constant. Okay. Anything else? Okay. Oh, I will go back to lecture handout 3. And we've been talking about the particle in the one-dimensional box. We talked about the energies last time. Then here we come to something which is very similar to the homework problem. What value of A is required for the function to be normalized? Excuse me. Where we have established that the wave functions are A times the sine n pi x over L. Okay, what we've just seen from the question about the homework problem is that we have to integrate this function times itself, or we're integrating psi squared, again, because this function does not have an imaginary part. The complex conjugate is the same as the function. And we know this function only goes from 0 to L. Okay, that won't be the case here. And that will be A squared sine squared n pi x over L dx. I don't know why everything is blue. Oh, there we go. All right, and I've observed that here the helpful formula is this. Okay, let me erase some annotations down here at the bottom. Okay, re-summarize. Right below the formula, I will write the integral of a squared sine squared n pi x over L dx. We only have to worry about x from 0 to L. Okay, and the antiderivative can be inferred from the formula. So again, a squared is on the outside, but the antiderivative is 1/2 x minus 1 over 4a. A looks like it has to be 4n pi over L. Oh, and I will sloppily turn this 1 into sine of 2ax, which of course is 2 pi x over L. Oh dear. Bring it down here. Minus 1 over 4 n I over L. Sine 2 n I x over L. Okay, and again, this whole thing, 1/2 x minus sine 2n pi x over L over 4n pi over L is being evaluated from L to 0. Okay, if you look at the first term, that's 1/2 of L, plugging in L for x, minus 1/2 of 0, which is a 0. All right, minus 0. If you look at the second term, plug in L. Plug in L over here, it's soon sine 2n pi x over L, or sine 2n pi L over L. That cancels, and we have the sine of 2n pi. And we always know n is a whole number. No matter what value of n you plug in, you get something like sine 2 pi, sine 4 pi, sine some whole number of pi, or even number of pi, and you know that's a 0. Likewise, if you plug x equals 0 into the second term, that's also a 0. So this whole expression simplifies to a squared times L over 2, in this case. Set it equal to 1. And you find this factor to multiply in front of the wave function. Questions here? Okay. Oh, go ahead, Corin.
Can you rewrite the last number that you wrote down? I couldn't really see it from the bottom.
Let's see. Oh, down here
It
at the
was like,
bottom, the answer here.
yeah, it was like 1 over something. I can't see it.
Oh, are other people having trouble seeing that? It says 2 over L to the 1/2 is the normalization constant.
Okay, thank you.
Oh, okay. Couple questions in. The answer it came out is A, for any value of n, is 2 over L to the 1/2. Somebody wants a recap in the reasoning behind the steps. Okay. Reasoning behind the steps is when I integrate, I have to get a 1. And I know that I'm integrating from 0 to L. And I know I'm taking the square of the wave function. Okay, so all this leads me to this down here. What I've done is what I did was factor A out of the integral, and then I integrated sine squared n pi x over L. I used this integral table antiderivative to do so. Okay, so first I looked at the term 1/2. I took 1/2 of L, because we're integrating from 0 to L, and this is the antiderivative, minus 1/2 of 0. So that gives me terms 1/2 of L minus 0. Okay, then move over to the second term, which is the sine function. Again, that's integrated from L to 0, so I plug in L, and that gave me sine 2n pi L, well, 2n pi, which is 0. So the third term is plus 0. And then I want to subtract the value when I put in a 0, and that's sine of 0, which is also a 0. So actually, I had to worry about the first term from L to 0. Then I had to worry about the second term from L to 0 in my integration. But that, as you see, produced 3 zeros, so the total sum was 1/2 L, or L over 2. Setting a squared L over 2 equal to 1 gives me a value of 2 over L to the 1/2 for A. Okay, so another way to recap this, A is the value it is because that is the value necessary to make the integral of the probability function come out to 1. Okay, I hope that helped anybody, or everybody. Let's try again. Did I get everything?
You
Okay.
you mentioned that 2n pi equals 0. How does that work?
Okay. N is number 1, or it's the number 2, or it's the number 3, or something right there, right? Right? Okay, so stick in a 1. All right, so then we have 2 pi x over L, and we're evaluating at L. When you plug L in, x is L in the numerator, and in the denominator, that cancels. So you just have 2n pi. If n is 1, it's the sine of 2 pi, which is 0. If n is 2, it's the sine of 4 pi, which is 0. If n is 3, it's the sine of 6 pi, which is 0, and so on. Does that answer the question?
Yes, thank you.
Okay. Anything else? Okay. Let's try a similar one in question 3. The average value of the position in the n equals 1 state. Okay, and I have a helpful formula down here. Turns out you'll remember that the position operator in one dimension is just multiplied by x. Okay, so first you have to ask, well, in principle, is psi an eigenfunction of the position operator? And hopefully you can see from the form of psi that psi is not an eigenfunction of the position operator. Remember, in particular, for the n equals 1 state, which is what we're interested in, I'll call it psi 1. The wave function is 2 over L to the 1/2. I better erase that. I'll come down here. All right, the wave function in the n equals 1 state is a, which we now know is 2 over L to the 1/2, times the sine of 1, because n is 1, is pi x over L. Or even write it this way. Okay. Okay, if you multiply by that x, it's just been multiplied by x, and x is not a constant. So hopefully you can see, without further discussion, that it's not an eigenfunction. Okay. In this event, you need to take an average or expectation value of the position. Here, I'll erase this, move it out a little bit. And these average values typically are indicated by brackets like this. And maybe you've seen this in a statistics class, and it popped up a couple times last semester. To find the average value, which is pretty sort of the best you can do, except unless you are doing, unless you have an eigenfunction available, you have to make a sandwich integral of the complex conjugate times x times the wave function. And that will tell you, since the value of x is a statistical thing, that will tell you what the average position is. Okay, so in the case of 2 over L to the 1/2 sine pi x over L, that integral looks like, oops, I need to move again. The integral, again from 0 to L, because in this system, those are the only possible values of x, of 2 over L to the 1/2 sine pi x, whoops, over L times x, I'll put it in parentheses, times 2 over L to the 1/2 sine pi x over L. Okay. Whoops. The scheme in general here is to figure out an integral you have to do, simplify it, and then use one of these handy formulas from a few pages back to solve the problem. Are there questions about how I got to this point? Again, basically, I took the complex conjugate of psi, which is the same thing in this case, multiplied it by x, and multiplied again by psi. So we have this sandwich type integral where x is sandwiched between two sides. Okay, then I can simplify a bunch of stuff. Pull a couple 2 over L's to the 1/2 out. We've got 2 over L, and I'm integrating from 0 to L x times sine squared pi x over L dx. Okay, then we look at the formula and go, oh, this must be this thing where A is pi to pi over L. Okay, I'm going to clear annotations. Okay, the answer is the integral from 0 to L. Whoops. Now, let's make life easy. Start out with 2 over L. Then we have the integral from 0 to L of x square of sine pi x over L dx. And that's going to equal 2 over L, open paren, x squared over 4 minus x sine 2 minus x times the sine of 2ax hopefully clear a has to be pi over L. So we have the sine of 2 pi x over L. And, I'll just write 4a in the denominator. We know what a is. I wrote it right up there. Minus the cosine of 2 pi x over L over 8a squared. And once again, a is pi over L. Okay, and this whole thing is getting, again, it's the antiderivative, so we take the value at L and subtract the value of 0. Okay, if we look at the first term, squared over 4. If we plug in L, we get L over 4. If we subtract the value at 0, we're subtracting 0 squared minus 4, which is 0. So the first term provides values of L squared over 4 minus 0. The second term is a sine term again. If you plug in L, you're taking the sine of 2 pi, which is 0. If you plug in 0, you're taking the sine of 0, which is 0. So plugging in L and plugging in 0 both give zeros in the second term. Okay, if you plug L in for the cosine of 2 pi, so you get cosine of 2 pi, which is 1. If you plug in 0, you get cosine 0, which is 1. So this is minus 1 over 8a squared plus 1 over 8a squared. Okay, which means the answer is 2 over L times L squared over 4, or L over 2. Okay. Questions here? If you sketch psi from 0 to L, it's a sine function with a big bump at L over 2. So it makes sense, without thinking about it, that a sketch of psi squared, since psi is always positive, must have the same general shape. And this is a bump that peaks at L over 2 and is symmetric on either side. In other words, our answer makes pictorial sense. Questions here? Okay. Now it wants the average moment value of the momentum. Again, sine is 2 over L to the 1/2. It's the n equals 1 state again, so sine pi x over L. And I circled a helpful formula, which we'll talk about how it's helpful, hopefully here in an instance. How, and feel free to type it in or answer out loud. How would you start this problem? Oh, I'll remind you that the momentum operator in one dimension is h bar over I times the first derivative operator. Is psi an eigenfunction of the momentum operator? I'll answer that one. When you take the first derivative of psi, it's going to turn to cosine, which is not what you started with. So the answer would be no. So once again, we need to calculate an average value. And that means making a sandwich integral with the momentum operator between psi star and psi. Okay. I'll factor the 2 over L's out, with the 2 over L's to the 1/2 out. 0 to L sine pi x over L h bar over I times first derivative operator, which, since I factored out 2 over L to the 1/2, operates on sine pi x over L. I can pull all the constants outside. When I differentiate sine, I get pi over L times the cosine of pi x over L. All right, now I have a pile of constants out front. 2 pi h bar L squared I. Times the integral of the sine multiplied by the cosine of pi x over L. All right, now I can open paren, and the argument being, or the value of A in the formula is once again pi over L. So I'm taking 1 over 2 pi times L times the sine squared of 2 pi x over L evaluated at L is 0. Okay. What is the answer? Both the argument at 0 and L equals 0, so the total is 0. All right, questions? Okay. Last exercise shows the two states were orthogonal. Briefly, orthogonal means that if you multiply the complex conjugate of one by the other and integrate over all possible values, you get a 0. I have the hint formula here. I think I'm going to leave this one as an exercise. In other words, this one will probably be on the next homework. Okay. I think I'm going to pull lecture handout 3. And move on to lecture handout 4. Okay. Videos may be helpful. To review a bunch of the stuff we much did and get clues on what to do with the other problem I didn't do. I said I would assign something like that or similar. Here are demo videos deriving the energies of the particle in the box. If you look at this 1130 onward, there are exercises in normalization and orthogonality. And there are videos for finding the average or expectation values of x and of the square of x. In addition, both of these links show you how to set up the problem, but not how to solve the integral for the average value of the position and the average value of the momentum in the particle of the one-dimensional box. This model system, the one-dimensional box, we're on page 3 now, readily extends to any number of dimensions, 2 or 3 dimensions being common extensions. Okay, to define a particle in a box of multiple dimensions, like 3 or 2 dimensions, for example, you simply require x to be stuck between 0 and some value as before. And if you want to add a variable, you add a variable y, and you trap that between 0 and Ly. So if you add 2 variables, you can imagine a box of 2 dimensions, for example, which is essentially a rectangle of length Lx times by Ly. And the particle would be stuck in the rectangle. So in the box I've drawn, Lx is longer than Ly, for example. Okay, then all you need to do, now, since it's a 2-dimensional function, psi is a function of x and y, But all you need to do is add a term to the Hamiltonian. Here is the first term for the second derivative in x. Here is a second term of the operator for the second derivative in y. If you want a third dimension, you add a third term for the second derivative in z. In principle, in a mathematical game, you can go on adding terms for a fourth dimension, a fifth dimension, etc., and so on. Oh, by the way, this figure is stolen from Blender, where in this case, psi to the r means psi is a function of, since Blender does 3 dimensions, x, y, and z. Okay, since the energy, kinetic energy of x and the kinetic energy of y and the kinetic energy in z are all separate, this separates into 3 functions: a function of x, a function of y, times a function of z. Like the allowed energies follow a similar formula. If L is xa squared, if A is Lx, and B is Ly, and Z, adding a third dimension, traps a particle in a 3-dimensional parallel pipette, then here is the formula for the energy, where you have 3 quantum numbers, nx and y, and nz, all 3 of which may be any whole number. Okay. Particle in the 3-dimensional box is well used in advanced physical chemistry, for example. We can start out with 3-dimensional box wave functions. Treat each particle in ideal gas as a particle in a 3-dimensional box. And by summing up all the particle energies and by careful analysis, we can get to the ideal gas law. This is sort of discussed in Chapter 3 of Blender. In the meantime, here's an energy formula about the particle in the 3-dimensional box. And you will be given an opportunity to practice plugging quantum numbers and box lengths into it very soon. At this point in most PChem texts that the concept of degeneracy is brought up. Okay. Degeneracy is when you have 2 or more states with the same energy, and it often arises when there is some symmetry in the system. For example, imagine that the room you are in, or the room that the gas particle is in, is cubic in shape. In other words, that it has the same value in each dimension. If I call all these things L, for example, then the energy up above is h squared over 8ml squared times the square of the x quantum number plus square of the y quantum number plus square of the z quantum number. Okay, if you just set the z quantum number equal to 1 and let nx be 2 and then y be 1, the symmetry of the system, because all the box lengths were the same, means this has the same energy as z is 1, x is 1, y is 2. In other words, the energy of state 2, 1, 1 is the same as the energy of 1, 2, 1, where we list the x, y, and z quantum numbers in order as subscripts. Okay. Questions here? Okay, I'm electing to stop here at this point, since there are a few minutes extra. I don't want to start the next model system, which is the harmonic oscillator, just yet. I will instead give another opportunity for questions on any issues in homework 2. Okay. If there are no questions on homework 2, we're going to pick up, will we still be able to do question 6 without the harmonic energy operator lecture? Oh, yes, that's a good question. And let's go to number 6 while we're here. Okay. This is the harmonic potential energy operator, V equals 1/2 kx squared, or multiplied by 1/2 kx squared. All you need to know for problem 6 this operator is going to show up in the harmonic oscillator model. And well, you don't even need to know that. You just need to know the form of this operator V and the form of the operator P. And then I would just, follow the hint. First, let V operate on some function F, and then P. And then let P operate on F, followed by V. And take the difference of the result of the two things. So this one is easy, for example. I'll start you on this. V of PF is V times H bar over I times take the first derivative of F and if I label the first derivative of F prime, and V just is multiplied by 1/2 kx squared, then the result of doing P and then doing B is H bar over 2I times F. I did something very similar in Thursday's lecture. Oh, I believe it was not Thursday's lecture. I believe it was Tuesday's lecture where I talked about the uncertainty principle. Can I take any other questions? Okay, I'm going to stop the